Hi guys, my name is Jen and I'm going to be teaching you deep learning. So let's go ahead with what deep learning is and just an introduction on what is deep learning, what is the definition, etc. So deep learning is an incredibly important part of artificial intelligence, and semantically, or in a lot of literature, you will see the words used interchangeably. But the superset is the field of artificial intelligence. Many companies also use it as data sciences. So that's like the mother. So on the high level, on the highest level, we have artificial intelligence and or data science. From that comes first the field of machine learning or field of simulation, field of other fields, etc. And within that is a subset called deep learning. And why is it deep? What is actually deep? So that's a simple reason. One of the first ways, so some of the earliest algorithms of this practice of neural networks or deep learning came way back in 1950s. Yeah, that's very, very surprising. But so in 1950s, what happened was some of the most famous scientists of that time, I think we'll see a name as we scroll down. So what they did was they were really inspired by the brain. And when you say brain meaning not just the human brain, but could be an ant brain, could be a brain of a mouse. These are very complex beings. There are a lot of parallels from biology or or nature that a lot of neural networks have been built. So the scientists figured out that the brain of a rat or a mice, if trained properly, mice can detect bombs. Mice are also nowadays being trained to figure out which paintings are more beautiful, etc. So they are incredibly complex beings. And as you know, ants also have like a queen ant, and there are like 10,000 or lakhs of ants that live beneath. So basically, what I'm trying to sort of hint at is that there's an incredible amount of complexity just by using simple brains or neurons. Now, what is a neuron? As you may recall, way back in your high school biology, neuron is a simple structure that resides in your brains or in your neural network. In a human or in an animal neural network that receives an input and sort of spits out either a 1 or a 0, meaning yes or a no. So let's say you touch a hot object, a hot tea, and then suddenly your hand goes back. That's a reflex. That's powered by neurons saying, something detects saying that it's hot and I need to sort of move away. So that's a simple application. If you have your dog, it knows when it smells a familiar, its master, it says to be friendly or not friendly. So that's very, on a basic level, what a neuron does. Mathematically, to simplify that, basically a simple node of a neuron, what it does is it simply fires a 1 or a 0, which is a true or a false kind of state. So like he's saying here, neural networks are inspired by the structure of the cerebral cortex. And at the basic level is a perceptron. Now, what is a perceptron? So a single neuron or a single layered neuron is called a perceptron. Now, what is a layer? This is a simple neuron. And now if I have like this whole, like if I collect 4 or 5 neurons in one layer, that's called a perceptron. Some people also fondly call it one-layered perceptron. And as we'll get to this, but it might be useful to speak a little bit about this. Deep learning is nothing but something that's deeper than 2 or 3 layers. That's it. That's all there is to deep learning. And we'll see why does it make sense to have one layer, or maybe one neuron, multiple layers, or deeper. What is the advantage or disadvantage of going deep? So at the basic level is the perceptron. And like I said, the mathematical representation is a biological neuron. The first layer is the input layer. Like I said, so each of these nodes sort of takes in an input and it spits out one output. Now, a combination of these obviously will take a set of inputs and a set of outputs. So this is a simple 2-layer deep network. Now, why am I calling it a network? As you can see, it's a small net. Some of the neurons are interacting with the others. So what happens is typically a neuron tends to interact only with the layers, the layer in front of it. So it can interact with any one of these layers, right? It cannot, however, interact with this layer. That's the way they're designed. So meaning it's sending something like ones or 0.5 or something, some set of information to the network in front. And finally, they all sort of flatten or coalesces to one output layer. Now, what is that? That could be again a binary decision. It could be true, false, and if I have like 2 or more output layers, it could be a lot more information, a lot more classification. Like for instance, it could be cat, mouse, table, etc. So basically, an architecture consists of just 3 things. One is you have the input layer, which take in all the inputs, and you can say, do I want 6 of them or do I want 3 of them? And there are hidden layers. Here the number of hidden layers are 2. Hidden layer 1 has 4 nodes, hidden layer 2 has 3 nodes, and there's 1 output layer. So that's it. That's pretty much deep learning is. That's it. So there's an input layer, there's a hidden layer, and there's an output layer. And if I have just one of them, it's a simple perceptron. So deep learning is a set of perceptrons built or stacked over each other, layer over layer over layer over layer. In fact, one of the better libraries available out there, which Google wrote on top of TensorFlow. So TensorFlow is one of the 4 or 5 libraries we will come across that Google has sort of written and very graciously open source. So Keras is a higher level library on top of TensorFlow. Most of the library is sort of nomenclatured saying sequential. So why is it a sequence? Why is it sequential? Simply because each one of them is in sequence with the preceding one. So Padam asked a very nice doubt. What kind of problems cannot be solved using ML, and when do we need to use deep learning? Excellent. That's so this sort of insight is going to pretty much change what's going to happen. So machine learning, historically, the first machine, and I want to give a little bit of narrative that will help you understand what's happening. ML fails spectacularly in 2 areas, or where deep learning is in full glory is in 2 areas. One is vision, second is speech. What vision means is talking about images, videos, so on and so forth. And speech means text, voice to text or voice in itself, etc. And I'll give you the sort of, I hope that answers on a high level the question. And I'll give you a little bit of backdrop. Some of the most earliest ML algorithms, like the naive Bayes, was there way back in 1850s. And up till recently, most of your Bayesian spam filter in Google was written on naive Bayes. And however, the accuracies of your typical SVMs or logistic regressions or a classic decision tree, etc., sort of tapered off in many of these problems in the 85s segment. But Jeffrey Hilton sort of came in 2012, and he made a very powerful deep learning network and sort of changed the whole contour. He's called the father of AI. The for the same image recognition or text mining problem, what was in conventional machine learning algorithms around 85, he pushed it to almost 95%. And that's like a quantum leap. And everybody was astounded. In fact, I know one case study for sure. So Shadi.com, way back in 2008, was one of the first companies in India to use machine learning to detect faces of grooms or brides, and then sort of recommend matches. So based, if you are tall and if you're like, of fairly decent complexion, then you would be matched with recommended people, similar people. One of my friends went ahead and uploaded a chimpanzee photo, and he was obviously also recommended good people. So that's one of the drawbacks of machine learning. And they were using machine learning algorithms because they sort of had to measure. They measured the distance between the eyes, the size of a good nose, the width of your face, height. But AI or deep learning does not use any of those. Today, if you know how well Facebook uses image tagging, etc. So deep learning is really good in those other fields. Moving on. What is the scope of deep learning compared to machine learning in India? Actually, very less. My experience, people might have a different view. I've been sort of really looking for rich deep learning problems, and it's very less. Only a few of the top companies are doing cutting edge work in deep learning. For instance, I know for sure Flipkart's trying to do something with their white label product. They're doing some really good work in deep learning. Although machine learning also has been only recent. So many machine learning, for instance, the banks, fraud detection, credit cards. I know for a fact Citibank and American Express India use a lot of machine learning techniques. They've been doing that since 3-4 years. If you want to really work for good deep learning projects in vision, in speech, you might have to look at outside India, namely like the Bay Area or Singapore or London. Simply because deep learning uses something called GPUs. The computational power is like very high for GPUs. GPU is a graphical process unit. Whenever you watch a movie or play a video game on your laptop, a GPU is invoked. I'm sure you know this, but whenever you do like this video recording or something else, a CPU is used. And GPUs are very expensive. So most companies can't really afford GPU space. But deep learning is the future. I mean, you're in the right place at the right time. It's definitely going to peak by 2020. So it might help to be part of something that's going to grow in 3 years. Yeah. So think of deep learning as a technique for learning in neural networks that utilizes multiple layers of abstraction to solve pattern recognition problems. Now, what is abstraction? So the word abstraction is very important because a lot of machine learning problems have a high element of explicability. For instance, when you know a decision tree sort of splits on age or splits on gender, etc., you know that you can explain it to a client. But for a long time, for more than, I think, 8 years, nobody knew how or what was going on in each of these hidden layers. What is this math? What was the science going on? What was each layer I'm trying to understand? What was each perceptron doing? Nobody really knew. And even till date, some people are doing PhDs on trying to understand what's going on. But so that's why there's a lot of abstraction. So in many instances, for instance, if you take a regular data and trying to predict like the price of housing prices in Bangalore, and you have like 100 features, and you apply a deep learning problem on that. Nobody really knows what's happening in the middle layers, but the accuracies are fantastic. Similar with credit card industry, where I've worked in extensively. Fraud is picked up, but nobody knows why it's picked up. So there's a lot of abstraction. People are still learning why it's happening. In fact, if whoever is interested in PhD can sort of do it. It's a 5-year course. Yeah, so in the 90s, 80s, most networks were a single layer due to the cost of computation and availability of data. So just as a refresher, for machine learning, we had 2 broad classes. One is supervised learning and unsupervised learning. Similarly, even deep learning has 2 classes, supervised and unsupervised. Supervised is where you have a target label, prediction of fraud, prediction of housing prices, etc. In unsupervised, you obviously don't know what you're trying to predict. You're trying to get like a very high first cut, look for patterns, investigate for classes, etc. And then maybe on top of that, go in and then do a supervised learning. So one of the particular, so this might be a noteworthy moment to mention something. So in particular, deep learning also sort of caught the whims and fancies of all classical machine learning people or scientists. Is deep learning has a really good technique called autoencoders. We should be looking at that in, I think, third or fourth lecture after the session. So autoencoders are an amazing way of unsupervised learning. We look at that a lot more deeply, and that's sort of taken the fraud insurance industry by storm. They are far more powerful than rules mining, clustering methods, etc. Yeah. So most of you have probably heard about AndroNG, and AndroNG it runs Baidu's, or used to run Baidu, one of China's largest companies, AI module. He has amazing courses on Coursera on deep learning, etc. Why does he think deep learning is very important? So deep learning particularly sort of shoots through the roof again when you have more and more as the size of data increases, and obviously the volume and the velocity with which data thanks to big data, the volume and the velocity of data is increasing astoundingly in the world. You have so many Facebook photos, so many Snapchats, etc. Particularly as the size of data increases, you get a lot more performance. But the legacy machine learning algorithms sort of have taper off after reaching some size and volume. And also they become exceedingly slow, which is also a problem in deep learning. Like I said, computer vision is one of the most hallmarks of deep learning. So you've seen, like I had mentioned, you've seen a lot of brilliant use cases by Facebook in identifying faces. Nowadays you can tag, it recommends tags, which is amazing. So this is a very famous problem where people measure the accuracy of your deep learning algorithm. It's called ImageNet. So the ImageNet problem in deep learning is a hallmark. And let me tell you a story there. So ImageNet is a competition started by people at Stanford, wherein you have 1 million images of cats, dogs, Egyptian cat, you have African American, you have bus, train. So you have you have more than 1,000 classes and 1 million images. So a human accuracy is roughly at around 85%, like I had mentioned. Sorry for the typo here. And for the longest time, machine learning algorithms were roughly around 80% or 85%. Now, when Geoffrey Hinton, the father of AI, he came in, the accuracy, he used a two-layered deep learning network and also another technique called convolution. And that result got pushed to 91%. That was astounding, and people went gaga over it. This was as back as 2012. At the time, he was a scientist professor at the University of Toronto. What happened a year later was Microsoft just went ahead and said, instead of using a two-layered network, I'm going to go deeper. I'm going to go 50-layered network. We look at that, what happens. So, and then with the 50-layered network, which is just heavy brute force, as the network depth increases, obviously computational intensity increases, and hence the electricity, the cost increases. So just by brute force, Microsoft went in and pushed the accuracy from 91 till 94%. And that was like, people went again gaga over it. So Microsoft won the ImageNet competition in 2013. Now what happened in 2014 was the Oxford group came in and they again pushed that to a 100-layer network, again brute force, and pushed the accuracy to 97%. I think right now, state of art, Google or I think Google won the competition, ImageNet, and they're at 97%. That's astounding. So I think, was it Google or Facebook? Yeah. So that's at 97%. And we're talking about like complicated cats. Like not many people can really know the difference between Egyptian cat and some Persian cat. But computers with deep learning techniques are getting it right. So that's what Facebook uses also internally to distinguish what's you from a friend of yours. Again, like I said, speech is one of the most affected areas. As you might have used Siri, Echo, etc. Again, a lot of deep learning techniques can be used for other classical problems such as simulation problems, OR problems, etc. And Google has managed to cut their energy needs by over 40%. This translates to about 15% in power usage. And we're talking about a huge volume of power usage. Just a few use cases of DL again. Now, illustration tagger, that's an implementation of illustration to WEC. This service can tag an image with a safe, questionable, or explicit rating, copyright, or general category. Deep Filter is a style service for applying artistic filters to images. This is particularly important for streaming providers such as YouTube and Roku, etc. I think you might have seen YouTube sort of does have a small tag of copyright where you can't really plagiarize that easily. So again, a use case of DL. The next one is the age classifier. Again, this uses face detection to determine the age of a person in a photo. I'm sure you've looked at that. There was a small app. So what's happening on the back end is your face is being sort of compared with or benchmarked on a million other faces, and sort of it understands and sort of predicts what is your age. The Places 365 classifier uses a pre-trained CNN. Now, CNN is a convolution neural network. We're going to look at that next class, I think, in the next sessions. And based on places. An image database for deep scene understanding to identify particular locations in images. In drugstores, hotel rooms, etc. Yeah, it takes an image such as a car and returns the top 5 classes the model predicts are relevant to the image. What does that mean? So, like I said, Google won the recent competition, and that's called Inception Net. By the way, so Google's network is 150-layered network, deep. That's simply brute force. I mean, the amount of intelligence you put there is like not really that great, but it's just simple. It's true because it simply works because Google has a lot of muscle power and will to do it. So moving on. So it takes an image such as a car and returns the top 5 classes. Does anybody have a guess why should a car be predicted as something else? So just for illustration, when we take a car image, right? So this seems like a good image. This image can be classified as, I'm saying the question was, why should a image of a car have 5 classes? Here's an image of a car. Now, and I sort of have written here 5 possible classes for the same car. So the 5 classes are Suzuki car, that has a 90% chance. There's an 80% chance that it's a blue colored car. There's a 40% chance it's a hill. And a 1% chance it's either a river or it has 2 wheels. Does it make sense? So there are 5 classes that have been predicted, and the probabilities for each of them have been predicted. So that's how powerful Google's inception net is. So that's what I wanted to sort of illustrate in this direct implementation of Google's inception net. Take an image, and it also gives you each class and its probability. Now that we sort of have a good understanding of why, how powerful deep learning is, and also why feeding in a million images, etc., is really important. So there have been some of the larger companies have been really kind enough or gracious enough to provide open source frameworks, as they always do. So here are 4 open source frameworks which are widely used. I'll go in the order of popularity. So TensorFlow is the most popular, widely adopted, and a library with the vast amount of literature available online. So Google wrote TensorFlow on top of Theano. Theano was an older variant. It works beautifully well with Python and NumPy. It's highly parallel. It can be slow sometimes, but that's okay. Most of the deep learning algorithms libraries are slow. Theano is second most popular. Again, the academia level has sort of taken a lot of interest in that. It's very low level. Okay, I see what you're saying. Like if the hill probability is 0.8, that will not come as output when I'm searching for car. Very good question, actually. So it depends. It depends on the problem you're solving. So, for instance, if you take Facebook, and let's say Facebook was using the same inception net, and you're trying to tag a friend. So it's going to say, tag, there's a photo of you and me together, and Mahalakshmi is also there. And amongst the 3 of us, it's going to look at my face and say, this looks like Jayant. So, do you want to tag Jayant? In that case, what happened is the script was written in a way wherein there was Jayant as 0.9%, there was Mahalakshmi as 0.4%, Narendra Modi as 0.3%, so on and so forth. So, and we just wanted to have the top result. Sometimes we might need also the second result. I'll tell you a very new and upcoming area of science. It's called video annotation. So in video annotation, however, we really need more than 2 or 3 types of class output. So for instance, this is like a fairly new sort of area. So for instance, you see a video of, let's say, Kohli batting. So one of the top things could be batsman hit 100. The second one could be, although right, and the third one could be cricket ground. In this case, however, you might need to pop out the top 2 results. So it really depends on the use case, because more likely it's Virat Kohli hits 100 is what you want, right? So what I'm trying to say is there is no sort of set output. Output is really defined on the business use case. I hope that makes sense, guys. Yeah, but most often you're right that for classic images, you just pop out the first output. So DL4J is a JVM based, that's Java Virtual Machine. I have not used it. It's hardly used. Torch is very popular right now. I mean, it used to be less popular. but it's rapidly picking up simply because Facebook and Twitter have been using it. And as you know, whatever Facebook uses, it sort of imposes on everybody else. Lots of pre-trained models. Now, what are pre-trained models? We sort of looked at it before. We look at it in one, I think, chapter 4. It's called transfer learning. Pre-trained models are, and I'm going to give you I'm going to con you into thinking why it's very important. So what's happening is, ImageNet has 1 million images, and you want to know, was it a Suzuki car or was it a blue car? Now, each time, let's say you tag a Facebook friend, you're not going to do the whole algorithm. You're not going to search all the 1 million classes and then do it. So instead, what you're going to do smartly is you're going to train that network on this architecture. And let's say we use that small architecture which we looked at, just a 3-layered network, this one. And through some magic, we understood that, okay, it's classifying the images correctly. In this case, the Suzuki car or the blue color car. What we do is we store all those weights in a local system or in the cloud, wherever. And next time you have a newer network or a newer classification, we sort of just invoke that command. That's why it's called pre-trained network. And they work remarkably fast. In fact, now, I hope you have like a good understanding of that. In fact, now we have something called a mobile net. These networks have been trained by all, Microsoft, Facebook, using their clusters, using their infrastructure. But you come back and condense it and sort of store it on your mobile phone. And the next time somebody takes a photo, like of your house or a selfie, it uses the pre-trained network information to detect what that is. So that's the power of pre-trained networks. And obviously, images, pictures, all these are really, really pre-trained. Images of people, images of cars, images of streets. But you also have some areas where there's no pre-trained. Any guesses what areas might not be pre-trained? So let me help you guys out there. So I worked on a problem wherein it was a manufacturing company, and they were trying to detect cracks in the second stage of their production conveyor belt. So obviously, and these are very particular cracks that come in on each of the discs. And if there's a crack and it goes to all through the production unit assembly, there's a huge loss. And so if we had to intervene at step 2 and figure out the crack, we needed lots of images of cracks. So how did we go about and get them? Are there pre-trained networks for cracks? No, there's no pre-trained network for cracks. So we really went ahead and sort of kept some data entry people, got images of cracks, put a surveillance camera again, also got images of lots of cracks. We were only able to get about 100, 200 images. But that was enough to sort of, again, start the network. I'm trying to give you a flavor of the advantages of the flavor of the kind of problems that I've solved and the advantages of pre-trained networks. The other one's a cafe. Torch, especially PyTorch, is picking up, booming big time. Yeah. So now coming to the meatier aspects of what how or what happens on the backdrop. So just to set your expectations, this will be a little math intensive. So you'll have to bear with me through the rest of the session. Yeah. So like I said, way back in the 50s, the first model of a perceptron, a neuron, was sort of developed. So for each neuron, we have 3 components. The first component is your weights. Single most important thing, and they correspond to synapses or inputs. Synapses is a biological term, basically inputs. And the second component is an adder that sums the input signals. And the third component is an activation function. This is useful for determining when the neuron fires. Basically, yes or no, or more than that. So that's it. So each neuron at its basic is a set of weights, has an adder function, and an activation function. That's it. These three components are the building blocks of every neural network. So mathematically, what that means is a simple neuron is nothing but the summation of the weights and the input nodes. And just linearly expressing, it's sigma of wi xi. So if you had like a two network, we had 2 w1 x1 plus w2 x2. That's it. So on and so forth. So on the left are the input nodes, right? So they are xi's, usually expressed as a vector, and the strength with which the inputs are able to deliver the signal along with the synapse is determined by the corresponding weights. And the adder then sums up the inputs from all the synapses. Next, theta is a parameter that determines whether or not the neuron fires given a weighted input of h. So given h comes in and bombards that particular small neuron, and we have a function or we have a parameter called theta, and what it does is it just says, should I fire a 1 or no? So the activation function is using theta as a simple fixed threshold. So just for an illustration perspective, this is how it sort of looks. So you have x1, x2, and xn. You have the corresponding weights, and you add up all of them. That's h. You plug in h to your theta, and it spits out the output, 1 or 0. This is at a neuron level. Yeah, activation function, I'll tell you what the theta or what's happening in the activation function. So the activation function, for now, let's keep it as a function that just takes a set of input and outputs a 1 or 0. What specifically happens in the activation function mathematically, we'll figure out. So an activation function is very similar to the ones in logistic functions. It could be a sigmoid function. It could be a ReLU or a tanh. So I'll just tell you really quick what a sigmoid function does. So sigmoid is a function. Think of it as I'll show you a small graph that will help you. So sigmoid is a very important function in deep learning. All it does is it pushes something. It looks like this. That is the function shape. It comes in nicely from minus. It takes values from 0 to 1 first off. Its input values are from minus infinity to plus infinity. And it is a beautiful function to push something to either 1 or 0. So that's sigmoid. I'll tell you the mathematical formula for that as well. It's 1 by e plus, this is the function. 1 by 1 plus e power minus t. Now ReLU, I'll tell you these two. So actually, I'll tell you these three because so that it will be clear. And like I said, I assure you, deep learning is pretty much going to be clear with this. Now, tanh is a simple function similar to sigmoid with one small caveat. Instead of ranging from 0 to 1, he's going to make it minus 1 to 1. Guys, remember this? So notice that here, this fellow starts at minus 1. And the top part is the same. That's all. Sigmoid starts from 0 to 1. Tanh is from minus 1 to 1. Formula of tanh also, you can look, it's very similar. It's e power x. Guys, this is the formula. E power x minus e power minus x divided by e power x plus that. Okay. don't worry too much about the mathematical formula. Instead, most of the interview questions, and I've done a lot of interviews, trust me, I've taken a lot of interviews and I've given, they ask you for the shape of the function. Now, and I'm going to teach you a function that's revolutionized, particularly deep learning. So sigmoid and tanh, if you notice, the bounds are 1. So it's not going to grow faster than 1. Because even if you take 0.9 into 0.9, it's 0.81. So for a lot of time, even though the architecture was deep, we had the best computers, we had the best GPUs, accuracies were low. Then one person, I forget the name, I think after Hinton, or probably Hinton, because he did everything. He came up with a beautiful concept. In retrospect, if you look now, it's like, oh, even I can think of it. He came up with a function saying, I want it to grow faster than 1. So what he does is, he wrote a small function that's called ReLU. Now what ReLU does is, ReLU is a guy ReLU is max of 0, x. So whatever value is there at that time in that neuron or weight or whatever that particular thing, I'm going to say it's either max of 0, x. So this function looks like this. And just notice this very important point. Till 1, it's almost similar to sigmoid till 1, but after 1, it just grows very fast. As you can see, so if the value is 100, it will grow very, very fast. So approximations become faster. So that's the advantage of ReLU. We'll look at the full glory of ReLU when we are actually looking at convolutional neural networks. But basically, just to surmise, activation function, the job of that guy is, I take in certain inputs, I have a mathematical formula, and I'm either going to predict -1, 1 in case of tanh, or sigmoid means 0 or 1. In case of ReLU, 0 or S. That's all. And that will be the output of that particular neuron. So there are several other activation functions, but these are the most, like in all my experience of deep learning, these are the most important. In fact, ReLU and sigmoid are vastly used. I used myself tanh once or twice. Excellent. So coming back to the previous thing, a single neuron is not interesting. So here is a useful time for me to drop in a small concept. Not concept, but a caveat. So in fact, there is actually a journal paper, very, very powerful scientific paper stating that any function in the world can be approximated by neural network architectures and specifically using ReLU. Like that's how powerful ReLU is. You cannot achieve that. I mean, what also that it's not explicitly mentioned in the paper, but what that also means is two things. One, you can approximate any function in the world, given you can go infinitely deep. Like you can have 1 million layers, but in practice you can't. You can approximate with deep architecture and using ReLU, and B, that privileges are not there for sigmoid or the other functions. So that's a little bit about how amazing this can be. And I'm going to show you a very nice demo about that. Remind me in case I forget. It's one of the very good visual tools to understand how these networks work. So single neuron is not interesting nor useful from a learning perspective. Obviously, as we've seen, one neuron is only going to say -1, 0, 1, or sometimes 0, S. But a bunch of them build an architecture, they can approximate any function. So when the bunch of them combine, that's called a network. That's why it's called neural network. Artificial neural network, convolution neural network, recurrent neural networks. Learning takes place by changing the weights of the connections in a neural network and by changing the parameters of the activation functions of neurons. Yeah. So we looked at what weights are. Weights are how perceptrons are defined. So like I said, what is learning? Why does a network learn? So we were going to look at that in this next 15 minutes. What exactly is learning? And that, like I said, it'll be a little math heavy. So just bear with me. Perceptrons. So a collection of neurons along with a set of nodes connected to the inputs by edges is called a perceptron. A simplest neural network. It's also called ANN. Each neuron is independent of the others in the perceptron. Yes. In the sense that its behavior and performance only depends on its own weights and threshold values, and not of those for the other. Though they share inputs, they operate independently. So this neuron, and the other one. So each one of them is independent. Now let's say we had one more layer, like we saw a hidden layer 1. That's going to be independent from the first layer as well. The number of inputs and outputs are determined by the data and the architecture you write. Okay. Weights are stored as an n by k matrix with n observations and k neurons. And Wij specifying the weight of the ith observation of the jth neuron. Okay, well, that's fairly, those are the definitions. So I'll tell you what is really important here. This is where it will get a little interesting. So the way a simple perceptron or a learning algorithm is built is, we compare first the outputs Yj from each neuron to the observation target Tj and adjust the input weights when they do not correspond. Okay, and that difference is calculated as Tj minus Yj. We use this difference to update the weight based on the input and the desired learning rate. This results in an updated root or a weight. This is very important to understand how a weight is updated. Why it's done so is that's the science behind artificial neural network. But this step is important, guys. So we'll look at what a learning rate is as well. Great, moving on. So now that you have weights, so we started with some weights, some random weights, and after each step, we sort of updated the weights based on the input, the outputs, and some learning rate. The learning rate is called ETA or eta. After the incremental improvement, the perceptron is again showed that same input training data, and then the cycle is repeated. So there's another update. This process is repeated until the performance no longer improves. When I say performance, it could mean accuracy or recall or the loss function sort of tapers. Having a small learning rate, having a learning rate less than 1 results in a more stable learning rate. Okay. Typical learning rates are 0.1 to 0.4 range. Yeah. So the stability is traded off against having to expose the network to data multiple times. So what learning rate is doing, so there are two concepts here. I think you might have also come across momentum. It might be useful to introduce that here. So learning rate is how fast you want your network to converge. So initially, typically in best practices, this is a heuristic. What people have tried many times, and this is how they've just come across this. Initially have a high learning rate. So what that means, very fairly well, is I'm trying to understand as fast as possible, was it a cat or a dog or a car or a Suzuki? Was it a Suzuki car or not? Now, as time progresses, once I understood it's actually a car and not a cat, I need to decrease my learning rate. Now, that's when it becomes 0.1. Sometimes you see 0.01. What that means is I'm trying to know, okay, is it a blue colored car or just a car? Is it a car with 2 wheels or just a car? Does that make sense? It's really boils down to saying I rush first to understand if it's a cat or a car. Once I know that it's a car, I'm trying to again find out with a small learning rate what specifically it is. So that's how people sort of practically or pragmatically do it. Yeah, any additional input node is typically added to the perceptron model. It's a constant value, usually -1, 0, or 1, that acts analogously. This establishes a baseline input when all inputs are 0. That's just a edge case. Yeah. So this is the practical aspect. Learning with perceptrons. So first step, there's the two-step process. Initialize all weights to small random numbers. Okay, because remember the universal approximation theorem that I had told you before. Any algorithm can be approximated with an ANN, and for sure with definitely a ReLU inside. Now, second step, for each T in T iterations, compute the activation for each neuron. This is the activation for each neuron J connected to each input vector I. This is the formula. That's Yj. So Y is the output. That's either 1 or 0. That's it. And we have like a simple activation function as g of x, and h is the sum of the weights and the inputs. And the next iteration, just update the weights. So the runtime is mn. We're not really looking much at runtime. So here is like a good example of a logical function. So we'll do two functions, and you can maybe take a shot at the third function. So we look at AND, OR, and I think you'll have to do XOR. I'll first show you what. So the AND function is simply, you have 0, 0, that's 0, 0, 1 is 0, 1, 0 is 0, and 1 is 1. This is your AND function, typical AND function, right? So I'm going to be just going through some of the libraries. I think Matplotlib, Inline, NumPy, Pandas, up till and Matplotlib, you guys are familiar, so I'm presuming you don't have any questions, but feel free to ask me any questions. Now, Seaborn is a simple visualization library based on Matplotlib. Have you guys come across Seaborn? Okay, so don't worry, it just makes beautiful plots. SNS.set, so C1 has been imported as SNS. SNS.set just controls the aesthetics, like the margin color. SciPy is another optimization function. It's a library. You have widgets. The important libraries here are sklearn and obviously NumPy and Pandas. These are the three most important libraries. The rest of it is just plotting. Moving on. So here I have a typical AND function, like I showed you. The objective of this exercise is, can we write a simple network or an ANN that will approximate Y based on X1 and X2. That's the idea. So first thing is, I first generate 3 random integers. And I'm going to initialize the weights or the integers to very small numbers because they can be updated very fast in NumPy. So this is like a simple function. Yeah. Then I write a simple activation function for calculating GH. And that function is nothing but, if I do a dot product of the input and the weights, and if it's greater than 0, it's 1. otherwise 0. The G is an important function because that's the activation function that we have written right now. So it's different from the ones three that we looked at. So what it's doing is it's simply saying if I have inputs dot weight greater than 0, then it's equal to 1. Else it's 0. That's it. That's basically the AND function. Now this is a custom training function that we'll go through. We'll go through and see how the weights are actually being updated. That's the important part of this. So I'm going to write a small train function with 5 parameters. We looked at what inputs are. We looked at what the target is. We looked at what weights are. Weights are 3 values we have randomized right here. We looked at what ETA is. ETA is a learning rate that we need to give to that system. Iterations is something we'll look at, but it's intuitive. Iteration is the number of iterations I want for it to converge to those values. Do I want it 5, 10, 15, so on and so forth. So there's a small amount of play in learning rate and iterations. Yeah. So the first step in this function is inputs. I give C underscore inputs minus NP dot ones len inputs 1. So what is NP ones len inputs 2? I create a string of, I create an array with ones, and then I just concatenate inputs with that. That's it. That is what this function does, and I put it back on inputs. If we have any questions, we can really sort of look at this way. Yeah, there you go. Are we clear? And inputs is right up there. These were the inputs. Now the next step in that function is for the number of iterations I give, and in that I go back to my activation function, which is G inputs weights, and this is AND. Now weights, how do I update my weights? Remember the formula, weights is weights minus eta times the dot product of activation minus targets. This line is just simply, 1 second. This line is just simply this line. This guy. Okay, so just understand that I'm writing it right here. That's all this function does. And then I return my new updated weights. That's what train does. Okay, you can actually see the weights being updated real time. I just wrote 2 print functions so that you can see it too. So let's just try. So I have my inputs as AND x1, x2, target as AND y. Okay, and I've given the learning rate as 0.25 and iterations as 10. Let's see how that goes. So there you go. These were the weights, and like I told you, the weights sort of converge. What step did the weight converge here? Actually, at the second iteration. So we were quite lucky. We started at something as minus 8.9314, right? Was that first? Yeah. So notice here, we started at something so random. We started at this guy, minus 8.931, 10 to the power minus 5, and it quickly converged to 2.41, 2.499. So that's how beautiful the approximation theorem works. Let's start with some other weights. You'll see it will converge to that again. So I'm going to say hit other random functions. So remember here, it's 2.9, 10 power minus 5. So notice how even though I start with any 3 random weights, eventually the network, in the first time it took 2 steps to converge. The second time it took 5 steps to converge. It eventually converged to, the correct weights, which are 0.25, so on and so forth, 0.25, 0.25, 0.5. So that's how powerful a simple network can be. Now, similarly, okay, great. So the weights themselves do not predict the output. So what's really happening is, let's go back to this schema again. What's really happening is, I started with a few random weights. In the first iteration, I started with a few random weights. These are the weights. But they will predict the function that will be used. So in this case, we're trying to figure out the function and the network that will predict the output. We know the output, right? Here, what happened is, we have an AND function. We know the inputs. Whenever it is a 0 and a 0, it's 0. Whenever it's a 0, 1, it's 0. Only when it is 1, 1, it should be 1. So we know the inputs, we know the output. We are trying to find the network that will approximate this. Clear till here? Similarly, how this will be useful is, I'm trying to illustrate how a function learns on its own the correct weights so that it will predict the output. For instance, this was a simple AND where only 4 cases are possible, right? Tomorrow, we might have 1,000 images, 1,500 images of cats, 500 images of dogs. Now, the network will train on these 1,000 images. Now, when the new image comes in, we will know how to predict that, classify that as a cat or a dog. So, in this case, what happened is, the network started with random 3 weights. It hit the weights, it took the dot product with the inputs, which was 0, 0, 0. Then there was this activation function which we wrote, and then we know the output, which was 0. Now the weights did not get that output, they went back in, the difference, we updated the weights. Now with the new set of weights, what happened is, again we hit the input, went back in, looked at the output, what was the difference, we went back and updated the weights. This process happened 5 times for the second randomization. But this process happened only once because for the first random weights. Is that making sense? Maybe if I give it in a sheet or a matrix format, it will be better. Okay, see, so what's happening is, so I have here my x's. Okay, why is this not happening? Yeah, these are my x's. This was my weight. So the first weight was 2.02, 024, some random weights, 0.029, 0.004. Okay, I know the output. The output is, let's say the output was 0. Okay. Okay. So for 2 inputs, 0 and 0, the output is 0. This is an AND gate. Okay. Now for the first step, what happened is, there was an activation function here. We'll just leave it at here. So what it did is, it multiplied this into this, this into this. edit this, star this guy, plus this star this guy. So for the sake of simplicity, I'm going to remove one weight, okay? This for now. Okay, so this activation function predicted as this. There was something else here, like some exponential or something. So some function. Now, so this difference in weight, so one is different from 0, right? So it took the difference in the output. Then I went back in the function of how to update the weights and updated the weights. Let's say again, so this is the first iteration. So second iteration, what happened is, based on the activation function which we have here, so the inputs were the same, or we can give new inputs. It went back and it updated the weights. Okay, how did it update the weights? Based on the difference and the activation function. So now here, the activation function I took here a simple one, 0 star 2 plus this star this. Now here again it was this. Okay. So let's say hypothetically this was 0.3. So here's the difference. So this difference, now the difference is 0.3. Here the difference was 1. So now again the next step, I went back and updated my weights. So it became 0.025. Then this became 0.026. Let's say hypothetically in Y3, this guy became 0.01. And now the difference is much lesser, right? It will go on till the difference becomes 0. I mean, both the numbers must be very, very close. This is the third iteration. Guys, is this part clear? So I keep going on till I finally find smaller and smaller values of the difference. I keep updating the weights. Finally, we have weights with correct network with correct weights. So what is the correct weights here? The correct weights here are 0.25, 0.25, 0.5. So if I go back, so the correct weights here are, I'm going to write it here, 0.25, 0.25, and 0.5. So this weight in that architecture with that activation function will approximate an AND function. Now, no matter what I start with, it will converge to that. Let's again start with random weights. So just bear in mind, we started with 2.9, 10 power minus 5. Just bear in mind that. Okay. Now I'm going to again write start that function. Okay. 1, 2, 3. See, now it became 3.79, 10 power minus 5. Okay. Remember that. You see, how many steps did it converge? 1, 2, 3, 4, 5. Again, fifth step it converged, similar to previous one, but it will converge with the correct weights. So again, it converged at 0.25, 0.25, 0.5. No matter what I start with, I will get those weights. These weights in that particular function that we have written, that architecture will approximate an AND function. Okay. Similarly, OR. So OR is also very similar. You give the output, you give the inputs, and then it will approximate. So we start with random weights and then we go. So I think there's a small exercise you can do XOR. You can also do other exercise. XOR. What does XOR do? XOR. I'll tell you the formula here. For 0 and 0, it should predict 0. For 0 and 1, it should predict 1. So for 1 and 0, it should predict 1. And for 1 and 1, it should predict 0. So basically, it's not OR. Okay? Okay. So this is a simple scatter plot again. Like I said, so we did the AND example in class. And similar to that, I think you can do the XOR example. You just have to write one small, I can give you like the clue also. You just have to write the target as Y there and write the Y as that. And that's pretty much it. The rest of the code is pretty much same. If you have time, maybe we can do that in the class as well. Excellent. So this is a very good sort of feel about the same in graphical format. So here I have 1, 0. This is 1, 0, 1. So it has to be false. 0, 0, 1, 0, and green is the true spot. This is just graphically sort of how the network sort of separates it. Yeah. Moving on. So multi-layer perceptron is what happens when you are, like I said, you have several layers of perceptrons. Remember how we spoke about deep learning, deep network in the first half an hour of the lecture. So recurrent networks are something we'll look at session 3 onwards. We're going to look first at the latter approach. There are two kinds of approaches to add complexity. One is add backward connections so that the output neurons feed back to the input nodes. This is a recurrent network. We'll do that when we deal with RNNs. Second is add neurons between input nodes and outputs, creating an additional hidden layer, resulting in an MLP. MLP is multi-layer perceptron. Yeah, so similar to how you update the weights in a single layer perceptron, that can be extrapolated to a multi-layer perceptron. So there are two steps. One is you move forward through the network, that is in this direction. That's moving forward. Calculate the outputs given the weights and update the current weight estimates. The other similar way, another way to do the same problem is you move backward from the output error and update the weights. So these are two ways to go about a MLP. Now, what is more useful and faster is backward propagation, because it's important to update weights from the error. Let's deal with backpropagation. We'll explain what a chain rule is. So a backpropagation method is a very efficient way of computing the gradient of the cost function of a neural network. And we recall what we need to do with the cost function. Cost function is something that we need to minimize. So in case of a regression, our cost function was a simple sum of squared errors. So similarly, backpropagation is used to sort of compute the gradient of the cost function with respect to the parameters. Now, this is where it gets a little mathematical, and we need to sort of understand this, what's happening. Now, fortunately for us, a lot of clever sort of Russians have, and a lot of famous scientists sort of derived back propagation methods to figure out what error, how much of an error I need to take and assign it to which network. So for instance, in this, there were two inputs. There's one layer here and there's one output. Now there was some error that occurred at the final output. How do we know which of these nodes is the one that's affecting? Think of it like a very simple way. Today, your manager has few subordinates, and those subordinates have subordinates. Now, finally, a client, there was a deliverable and there was a mistake. The back propagation is a method wherein whatever mistake was made or error was made between the client and the boss, he will come down and he will effectively percolate it down to his immediate subordinates. His immediate subordinates will again do the similar operation and again cascade it down to who exactly did it within their subordinates. Finally, we will get to know which particular node did the maximum contribution of the error. That particular weight gets updated. So that is called the chain rule. If you have understood your manager and subordinate example, you have understood the chain rule. What chain rule mathematically does is whatever error in any, be it 2-layered network, 3-layered, or even like a 100-layered network, any error that is done on the 100th layer, 100th output, first you need to back propagate to the 99th layer, then come back to 98th layer, so on and so forth. And finally, it will come down to the first layer or second layer, wherever the mistake might be. It can happen, most of the mistake can happen somewhere in between, somewhere in end, wherever. But the important thing is that particular weight gets updated. Because it's fairly simple, it's very intuitive to understand that if there's an error created by, let's say, Jayant, it's not useful to update the weights of Padam. It's not useful to update the weights of Mahalakshmi. Jayant's weights must be updated as much. Then you recompute the error in the second or third iteration and then do the process again and again. This is what the back propagation and the chain rule does. For those of you who are very mathematical or have a deep understanding of this, you can go ahead and look at these formulas. This is a very interesting PhD topic in itself. Now I'll come down to so this is how the chain rule is. There's a rigorous sort of exercise here. So these are the three functions we looked at, right? So remember how I told you, these are the three Bible functions in any deep learning. Sigmoid, there are only three functions that are very commonly used. One is sigmoid, tan H, and ReLU. As I had shown you, these are the respective formulas. Sigmoid squashes. More importantly, this is an interview question asked several times. What is the range? 0 to 1. Tan H, I've told you, again, squashes anything, -1 to 1. ReLU, the deeper you go in networks, it's important to sort of amplify it. So it's max of 0, that number, that's all. Here are some typical cost functions, squared error, cross entropy. Here are the formulae for that. Cross entropy is used for binary classification dogs, categorical tasks, etc. This is how you compute cost the chain rule. This is how the chain rule is derived. So moving on, I wanted to show you. I think before the session ends, I wanted to do one example. I think this example we can take it up for tomorrow. as we are out of time, we can take up this practical example tomorrow. Here is one, I want one particular instance of. So you guys can open this, team, you can open this on your systems as well, this site, playground.tensorflow.com. It's a very useful site to understand how neural networks, deep learning actually works. So here you go. So first thing is I just have one layer. And this is the output function that I am trying to approximate, right? So let's go ahead and run one epoch. One epoch is one iteration. So it's like circles. I can change the input. So let's take a simple input like this. So it's done it really fast. And my activation function was a tanh. Even if you take a sigmoid, it does it very fast. And this is real time, so you can see the weights as well. There's a way to see the weights. Yeah, weight is 0.65, weight is 0.74. Now, let me take a little complex example. I'm trying to take circle. Let's see if it can do that. So clearly, it's not been able to do that because I have a linear activation. Let's try a sigmoid. Again, sigmoid, it didn't work out well. So what is the universal approximation theorem, that theorem state? If I increase the number of layers, then in theory, I can approximate any function. So as you can see, it's trying to understand where the red is and where the blue is, and trying to sort of figure it out. Let me put one more layer, and you can actually increase the number of neurons too. So let's increase the number of neurons. Again, it's trying to approximate it, but really didn't do a good job. So feel free to play around with this tool. So this, yeah, there you go. So tanh beautifully approximated it. That's a very good approximation of that function. Similarly, you have this. Not a great one, but yeah, eventually it came in. We just have a few points here and there. Let's make this network denser. Yeah, now this dense network really made. Let me increase the number of layers. You can also see the weights real-time based. That's really amazing. So this one was a perfect classification. You can see where deep learning also struggles. So this is a very complicated function, but remarkably, as you go deeper, it's trying to approximate it. So there are 4 very good functions on the left. The usual tips to what is the prerequisite skill for TensorFlow? So yeah, TensorFlow is actually quite, I would say, low-level language for Python, etc. I think so. I would recommend good coders to start with TensorFlow. But if you were how I started, like an average coder or somewhere where you were getting started, I would recommend Keras. So Keras is the high-level library written by the same team at Google. It's a wrapper around TensorFlow. So Keras is something that you can fairly quickly get started with. But knowing TensorFlow is like brilliant. Like if you know TensorFlow, you can straight away apply for Dropbox, Google in US or Singapore or London. We just take 2 minutes, and so that you get your hands a little dirty on that tool. Sure. So go to this link called playground.tensorflow, and feel free to sort of adjust the weights, approximate functions, and look at the learning rate, play with the momentum. You will know how deep learning sort of is actually at work. So let's do one quick demo here again. Let's try to approximate this function, which is a fairly simple function, with just 2 layers. As you can see, it's really fast. So regularization is actually, in this tool particularly, I think they mean making sure it's similar to the regularization parameter we have in our regression. It's trying to make sure that we have as simple as a function as possible. Oh, L1, L2, I was talking about regularization. Right? So L1 and L2 are our classic regularizations from Rich and Lasso. So L1 does basically the mod of the coefficients, tries to minimize the mod of the coefficients. L2 is minimize. So this is after the cost function. So minimize the coefficients square. So after that basic term, it's similar to the regression terms. Awesome. Okay, I think then that's all for today.
Acadgild. Average is dead.